The title of this presentation is Problems Preventing Practical Applications of Superhydrophobic Coatings. This presentation is part of the article which was published in American Chemical Society journal as an invited feature article. And it was published in 2020, last year. And now we are going to talk about the outline of the presentation. In the first part, I will talk about the lotus effect and superhydrophobic surfaces and expected industrial applications of superhydrophobic coating. Now, first of all, I have to describe what is superhydrophobic surface. What is a superhydrophobic surface? These surfaces were developed after 1990, and the number of publications in this field is around 15,000 at present. However, the industrial production of the superhydrophobic surface or coatings is very unsatisfying at the moment, although there are intensive research activities, especially in the last 20 years in many laboratories. In this talk, I will focus on some of the well-known but mostly overlooked scientific reasons of these unsuccessful industrial results. Now, in the second part of the outline, you will see that I will talk about the wetting sign and its relation with the superhydrophobic surfaces. The importance of the three-phase contact line around the drop and soil is very important, and it is sometimes overlooked in many publications. And because of the importance of the three-phase contact line, the contact area-based Wenzel and Kastel-Baxter equations were cancelled. So I have to talk about the reasons of this cancellation. And now, in the third part of the talk, I will focus on the industrial reasons. For example, there is a lack of the robustness and poor abrasion resistance of superhydrophobic surfaces, and their useful lifetimes are short because of the dust and dirt contamination from the environment. And it is sometimes very hard to obtain transparent superhydrophobic surfaces, but there are scientific reasons for this. And there are problems with the self-healing mechanism of the superhydrophobic surfaces. And superhydrophobic surfaces were applied as anti-icing coatings, but there are some reasons for their unsuccessful outcomes. And at the end of the talk, I will report on the conclusions and possible future studies on the superhydrophobic surface. And now, in the first part, superhydrophobicity is a well-known property in nature. For example, a lotus leaf repels dirt, and two German biologists, Bartlett and Neinhaus, reported that the water-repellent properties of the lotus leaf and also the flower come from the specific surface properties. They have a roughness on the surface, having two size range. In the first range, there is a cuticula around 10 micron size, and on the top of this cuticula, there are epithelial waxes, very small, tiny structure, has a dimension about 125 nanometer, very small. But this tool size range has to give the property to repel the water drop as a ball on the flower. And the water contact angle is larger than 150 degrees, and the roll-off angle with the tilt angle, which I mean, is less than 10 degrees. So when the water drop is rolling down, it is collecting the dust and dirt on the flower. So we always see a very clean flower structure. Now, the first low-cost superhydrophobic surface was obtained from a simple plastic. We used a cheap polymer, polypropylene, to produce a superhydrophobic surface for the first time in 2003. And this article is the most cited superhydrophobic scientists article with more than 1,600 citations in Web of Science till today. Afterwards, many articles were published on the production of superhydrophobic surfaces. In general, the methods to obtain such superhydrophobic surfaces can be divided into two main categories. The first one is to introduce nano and or microscale roughness and a hydrophobic substance having low surface free energy. And the second method is to modify a former micro-nanostructured rough surface by coating with a thin hydrophobic layer having low surface free energy. Now, so if I, excuse me, there's a problem with the page. Okay. Now I will talk about some possible applications of superhydrophobic surfaces. After the invention of such synthetic superhydrophobic surfaces, many industrial applications were proposed. For example, water repellent shoes, or for example, just from this is the water repellent shoes, and furniture cloths, or non-stick ketchup bottles, and self-cleaning of dust and dirt from windows by rain, as can be seen in this slide. Every kind of other applications are also possible. Water repellent and washable textiles, and more importantly, self-cleaning solar panels by water droplets are also very important. For example, in this picture, we see that the panels are cleaned by manually, but in this panel, which was kept in the laboratory, they are cleaning by only very small droplet on an inclination, and they clean all the dust particles from the solar panel. And many materials can be used as substances for superhydrophobic surfaces. For example, polymers, glass, metal, nanoparticles, or composites may be used as the substrate. And such superhydrophobic surfaces can be used in automotive, aerospace, textile, optometrics, medical devices, microfluidics, and marine industries. But the economic outputs of such products are not satisfying in comparison with the initial expectation. The reasons will be discussed in the next slide. Now, in this slide, we are showing the practical production of the superhydrophobic surfaces. After preparation of a solution, it is possible to apply dip and spray coating. This is the spray coating by the small spray, and this is the prepared dip coater, controlled with the controlled rate. And after obtaining the superhydrophobic surfaces, it is possible to apply optical microscopy, contact angle measurement, and the most basically the pencil hardness test. And now I will talk about the wetting sign, because it is a required step to understand the superhydrophobicity and outcomes of this sign. Now, first of all, we have to define the degree of wettability by using a water drop contact angle and a surface. Thomas Young was the first to report the thermodynamic equilibrium between the contact angle of a drop. This is the contact angle is a tangent, which was drawn from the 3-point contact line, and this is the resultant of the interactions of the 3-phase contact line between the solid surface tension and liquid surface tension, and the interpositive tension between them. Now, Thomas Young was the inventor of the contact angle, and he reported the thermodynamic equilibrium in 1805, about 200 years ago. Now, we cannot measure the equilibrium contact angle, which was also called by Young angle. We can measure in reality, we can measure the apparent contact angles. It is a bit far away from the equilibrium because it is very difficult to obtain equilibrium during contact angle measurement. But in practice, apparent contact angles can be easily measured. And it is also possible 2 types of different contact angles. One is the advancing contact angle while the drop is ionizing, and the other one is the receding contact angle while the droplet liquid is sucked and it is receding on the surface. These 3 contact angles are very important to characterize a surface. And as you may know, the hydrophobicity increases when the contact angle increases, and the hydrophilicity increases when the contact angle decreases, because it shows the interaction between the water molecules and the soil. And now we have to think about the factors affecting the magnitude of the water contact angle. In principle, the surface free energy and surface roughness are 2 most important factors affecting the value of contact angles. Surface free energy depends on the type and structure of the chemical groups on the surface. After the discovery of the lotus effect, we see that this is a hierarchy structure, that there should be 2 size ranged hierarchy structures to obtain superhydrophobic surface. And then the people started to apply 2 models, Wenzel models and Kassi-Baxter model, in order to describe the situation. Now, area-based Wenzel model was developed by Wenzel in 1936. When surface roughness is present on a solid And when the liquid fills the grooves on the surface completely, as you may see that the liquid fills the grooves on the bottom surface completely, then it's in the case that the actual solid liquid contact area of the surface is larger than its plane area. Plane area, you may see that the area which you look from top down to the surface. So the total area will be larger than the plane area. Then Wenzel suggested that for a given drop volume, the liquid-solid interaction is larger on a rough surface than that of a flat surface, and the contact angle can be calculated from the area value as a ratio between the real and plane area. This equation in the literature, the Wenzel model, is usually applied for superhydrophobic surfaces, having low surface roughness and strong interactions with the drop liquid. But the use of the Wenzel model is wrong. It was proven wrong in 2007. And the same applies for the Kassel-Baxter contact angle model. Kassel-Baxter contact angle model was developed in 1944. And this was developed for the smooth flat surfaces. As you may see, this is a fluid heterogeneous solid. The red and green showing the local heterogeneous stripes, but the surface is flat. And when chemical heterogeneity is present on a flat surface, the fields having different surface tensions from barrier against the motion of the droplet three-phase contact line. Now it means that while the droplet is moving on the surface, every green and red part interact with the liquid molecules with different strength, so they have different contact angles on the green part and the red part. The Kassel-Baxter equation describes this situation, and they use the area fraction for the solid surface. Now, it is also possible to apply the Kassel-Baxter equation for pattern superhydrophobic surfaces because these white places in this figure show the air pockets. So there is an air area. So we know that the contact angle of water in air is 180 degrees, and cosine 180 is -1. So this is the equation, very simple equation we obtain. Is the most used wrong expression for superhydrophobic surface because both Wenzel and Kassel-Baxter equations depends on the contact area, the magnitude of the contact area under the drop or beneath the drop. However, the contact area under the drop or beneath the drop is not important. The most important interactions occurs around the three-phase contact line. So area-based equation is wrong, and they have to be cancelled after the proof after 2007. Now, this is an old problem, but also there are many articles were published suggesting contact area based on Wenzel and Kassel-Baxter equations are wrong. The first article was published by Peace in 1945, and also Bartel is a very famous American researcher, cannot calculate contact angles by using Wenzel equations in 1953. And Ekstrand pointed out the Wenzel and Kassel-Baxter has many problems to be applied in 2002 and 3. But finally, McCarthy and his co-worker now made a proof how Wenzel and Kassel equations were wrong in 2007. And we also interested with the problem, and then we tested the regulations, the applicability of the regulations, and found that Wenzel is completely wrong, and Kassenbacher can give sometimes good results, around 50%. And these articles down to 2021 were already known and cited too much, but many scientists who are working in this Superhydrophobic science did not understand, and they try also report the use of Wenzel and Kassenbacher equations in the new publication. Now, the points, there are some points that Extrand rejected the validity of Kassi equation and pointed out the volumes of the contact angles are the results of interaction at the three-phase contact line of the drops are not dependent to the liquid-solid interfacial contact area. And McCarthy and co-workers made a proof by using very specific patterns. In this slide, you see that the patterns which were made by McCarthy group, and these are different hydrophilic and hydrophobic spots, and then they place water droplets in large area of small diameter or large diameter. So they follow the change of the contact angle according to the three-phase contact line diameters. And they prove that there is no effect of the contact area. So this slide is a very clear proof of the equation. Now, we also tested the applicability of Wenzel and Kassenbacher expressions, and we applied a simple comparison methods to test the contact angle results of the published 166 superhydrophobic samples taken from 6 different publications, and then found out that Wenzel equation did not fit the experimental results at all, but Kassenbacher case around 54, 44 or 65%, or sometimes around 50%, we can fit the results by the Kassenbacher results. And we also try to prepare our own patterns with the cooperation with the Middle East Technical University, and then published this paper in 2011. And then also the Wenzel was not valid. One Kassenbacher is also 88%. Cannot be used on our samples. There are 48 samples, pattern samples was used for this calculation. Now, I will talk about, in this part, I will talk about the main problems of the superhydrophobic surfaces, which they cannot be applied for the industry. Now, patterns containing needle-like structures are ideal to obtain a superhydrophobic surface, but they have very poor abrasion resistance. Small mechanical forces can destroy the texture on a superhydrophobic surface. Having micrometer or nanometer sized structures in the natural environment. This mechanical weakness is the main reason for the loss of the superhydrophobic properties in a short period of time. And then water droplets cannot roll off on the surface, but stick to the damaged location. And in the sandpaper tests with a long weight, pencil hardness tests, or adhesive tape filters and water droplet fall tests are applied for such purposes. And the second problem is the surface contamination and short useful service life of the superhydrophobic surfaces. The particles in the environment, in the medium, was absorbed on the surfaces. So the dirt, dust, volatile organic compounds, and substructive compounds can precipitate on the surface, and then it lost its superhydrophobic property. And if some superhydrophobic property was lost, then the self-cleaning is not possible. As you may see that the rolling drop goes out, but some dust remains on the surface. And now there are some difficulties to obtain a transparent superhydrophobic surface. Transparency is required especially for the windows and the solar panels, but unfortunately transparency and superhydrophobic properties are generally conflicting since light transmittance in a medium decreases with the increase of the surface roughness. Because of the mice scattering, especially in the roughness side, exceeds the wavelength of the visible light. So, in conclusion, a superhydrophobic coating becomes increasingly transparent when the mean size of the rough particles are less than 100 nanometers. But it is very hard to control such size. And there are drawbacks of the self-healing surfaces. Now, in the nature, many superhydrophobic plants and some insect can repair or grow new structures if mechanical damage and falling happens. But they try to apply the same method for the synthetic superhydrophobic surfaces. However, there are problems with the self-healing surfaces because both the presence of the surface hydrophobicity and roughness should be regenerated simultaneously, and this is a very difficult task. It was assumed that the movement of the hydrophobic chemicals having low surface tension to the air interface can occur automatically, but the box system should be sufficiently soft and can allow a high degree of mobility for this purpose. But if the matrix has weak, then it's a poor ability to resonate the surface roughness. Now, there are problems with the anti-icing application of surface superhydrophobic surfaces. It was experimentally proven several times that superhydrophobic surfaces do not repel ice. They can repel water, but they cannot repel ice. And if a superhydrophobic surface is kept in a condensation condition, in a cold condensation condition, and the solid temperature is below the dew point of the medium, then the water vapor condensation will occur in the surface microstructure, giving surface wetting and a strong icing behavior on the surface. So, also many articles published for the anti-icing superhydrophobic coatings. In practice, their success is very few. Now I have to make a collection for the conclusions of the problems. Now, as you may see, the use of the Wenzel and Cassidy-Box regression is not correct and must be avoided. The tiny structures present on a superhydrophobic surface has weak abrasive resistance. This is the most important problem. So they cannot be successful in the industrial applications for long term. For the transparent superhydrophobic surfaces, the mean size of the rough particle should be less than 100 nanometer, but it is very difficult to control or to prepare such a surface. For the self-healing surfaces, the simultaneous regeneration of surface hydrophobicity and roughness is a very difficult task for self-healing. And the use of superhydrophobic surfaces for anti-icing applications has been found ineffective, especially in humid below zero conditions. There are also the technical reasons. One is the most of the superhydrophobic fabrication methods reported in the literature are applicable for only small area surfaces by using high-cost materials. But these methods are not suitable for the large-scale production. And the long-term stability of superhydrophobic surfaces against contamination is often overlooked, but it is a very difficult problem. Now, for the last slide, we have some suggestions for further work. Most of the research on the superhydrophobic surfaces should be directed toward large-scale production methods with the use of less expensive and environmentally friendly raw materials. There is no need to use fluorine-containing expensive or environmentally harmful materials. The use of cheap and suitable functional polymeric or inorganic transparent primers or adhesive layers which can be applied between the target substrate and the top coat layer having superhydrophobic properties may be a good choice. For the transparent superhydrophobic surfaces, the use of primer adhesive layers containing small nanoparticles or bending very small nanoparticles into a transparent polymeric substrate by applying thermal methods are two promising approaches. For the cell-bearing superhydrophobic surfaces, the newly exposed layer should have a hierarchical texture with the hydrophobic chemistry after the mechanical and thermal regeneration. This is the end of my talk. I'm expecting your questions if there is any. I'm happy to meet with such an audience in the surface coating industry. Thank you very much.